In this video we're going to introduce the Boolean expressions associated with logic gates and logic circuits. Now when we looked at logic gates, I briefly showed you the equations associated with each of these fundamental gates, but we're going to revisit them in this video with a little bit more detail. So, for example, the most simple use of Boolean expressions is to describe a logic gate circuit. Right, in this case we're going to start with the simple gates themselves. So this is an AND gate, inputs A and B and output Q. Now I could describe the functionality of this gate using a truth table, as we've done in the previous videos. A, B and Q, 0, 0, 0, 1, 1, 0, 1, 1, and we know it's an AND gate. It's off at all times apart from when both inputs are high, A and B. Alright, but this is a little bit tedious to draw for every single one. And if we have, for example, 5 inputs, 2 to the power of 5, 32 rows, 2 to the power of 6 for 6 inputs, 64, these are going to get pretty complicated pretty quickly. So the alternative is, while we could use a truth table, we can also use a Boolean expression or a Boolean algebra expression. In this case, Boolean expression would be Q equals A multiplied, or A times B. So in the Boolean world, this is an interesting thing. We're going to write down, I'll just quickly write down the rules here. Boolean rules, multiply, in fact you can do that's the same as and plus is the same as or. And we can use a bar over the top of something to signify not. Alright, so just remembering multiply is an AND, a plus is an OR operation, and a bar over the top is a NOT operation. So, correspondingly for an OR gate, once again, rather than drawing out the truth table for this to describe the functionality, I could go Q equals A plus B, where we're not literally adding them together, but we're using the OR rather than the normal mathematical form of it. Right, both Q equals A and B and Q equals A or B fully describe the functionality of this gate, okay, as does the truth table, but it's a lot more compact and it's a lot easier to perform other useful operations like simplification from the algebraic form than it is from a truth table. So let's have a look at a slightly more complex example. Okay, so this is a 3-input circuit. Okay, we've got an AND and an OR gate. Now, we could go through and try and derive the truth table for it, but the easiest thing to do is just to write down the equation associated with the output of each of the gates. In this case, A and B becomes A and B here, and C. So Q becomes equal to A and B or C. Right, so a much easier way than having to go through and create the associated truth table. Let's do an example. We're going to do what's known as the majority counter example. And the majority counter basically has, if 2 or more of 3 switches are pressed, it could be in a game show or in a voting situation, then the buzzer sounds. Alright, so we've got 3 inputs, 1 output, and if 2 or more of those switches are pushed, then the buzzer is going to come on. So, oh, that one might be a bit long. I'm going to call my switches S3, S2, S1, and B for the buzzer. Now you'll note I'm doing a truth table, alright, just so we all get work from our 9 position. I'm going to use Martin's rule to fill in the possible combinations for our truth table. Alright, and so in this case we get if 2 or more of the switches, so this one, this one, this one, and this one, these ones are all zeros. Alright, so we've got a truth table that describes the operation of this. Often that's an easy way to start when you've got one of these word questions. You don't have to, but often it's an easy way. But typically the step you want to do next after you've got the truth table is then to write out the Boolean expression associated with that truth table. Right. You can go straight to the Boolean if you can see it that way, that's fine, but often it's better to go for this way. Alright, in this case I'm going to teach you what's known as the sum of products rule. So I'm going to do SOP, sum of products, and as it sounds, sum, so we're ORing together our products, our ANDs. And what we're looking for is all the conditions that the output goes high in. So in this case, I would write my expression as B equals not S3, because that is 0, S2 and S1, or S3, S2, S1, where S2 is not, or S3, S2, S1, and S1 is not, or S3, S2, S1. Alright, sum, okay, you can see my ORing here, of products, where these are all added together. Right, and so that would be an equivalent expression for this particular circuit. It may not be the most efficient one, which we're going to look at in the next video, but it is certainly a valid expression for this particular problem. The other way that we could write this is what's known as the product of sums rule. Alright, and in product of sums, rather than looking for ones, we're looking for zeros. So we now have B is equal to S3, S2, plus S2 plus S1. Noting that now we all together our inputs, and in this case when we're doing products of sums we have to invert them all. That's just the rule of it when we write them in this form, and you'll see we multiply together our sums. So once again S3 plus S2 plus S1, where we have, oops, sorry, I forgot to do my inversion. Alright, S3, S2, S1, those would all be knots, but we invert it in this form, so they all become normal ones. Okay, S3, S2, not S1, multiplied by S3 plus S2 plus S1. Next row, we get the opposite, so 0, 1, 0 becomes 1, 0, 1, effectively, plus S2 plus S1. In this case we have S3 plus S2 plus S1. Okay, so for this application, truth table that describes the operation, I've given you one Boolean expression using the sum of products form, and I've given you a second one using the product of sums. What you'll note from this is that there are multiple expressions for the same problem. Right? So that means there is not one unique way of writing out the solution to a general logic problem. All right? Sometimes there is only one, but normally there is more than one. So what you'll find now is that you can write for a truth table or a logic circuit, or even a specification, you may be able to write down an expression using Boolean algebra to be able to, or you're just using Boolean and logic expressions to be able to describe the functionality of that circuit. Remembering, even in rows like 0, 1, 1, when we were using the sum of products form, you cannot ignore the 0. You have to say that S3 is off, S2 is on, and S1 is on in order for the output to be on. Alright, in this form we're saying this must be true, or this must be true, or this, hence the or's in between. And the product sums we're saying this must be true inverted, and this must be true inverted, and this must be true inverted, and this must be true inverted. Different ways of saying the same thing. Obviously, if you've got a lot more ones than you do zeros in your output, then the product of sums might be more applicable to coming up with a simpler solution. Alright, correspondingly, if you have a lot more zeros than you have ones, then the sum of products might be a better way to write that circuit out.